Welcome friends to a session of finite element methods for fluid dynamics. I will be telling you about this course in this session. So that is the number for the course 618, and I am Sanjay Mittal. My office is in the low speed aerodynamics lab in the Department of Aerospace Engineering. My phone number is listed over here, so that is one way you can contact me. But the best way to contact me is through my email address. So you can write an email to me and we can schedule either a Zoom meeting or we can talk over the phone. So just to let you know what this course is about, it is essentially introduction to the finite element method and how it can be applied to fluid mechanics. Okay. So as you are aware that most phenomena in engineering, including fluid mechanics, can be modeled by partial differential equations. So in this course we are going to be looking at ways of modeling those phenomena as well as how to solve those partial differential equations to be able to understand them. Now obviously when you are interested in a numerical solution, some kind of an approximation will be involved. Okay. So there will be an error between what the exact solution is and what you would predict numerically. So most numerical methods would talk about error control, and in fact the philosophy of how the error is to be controlled is what distinguishes one numerical method from the other. So there are a host of numerical methods and a finite element is just one of them. Okay. So the objective of the course then is to provide you an exposure to the finite element method. It is one of the many methods to solve partial differential equations. And I hope that by the end of this course you would be able to figure out how to design a method to solve a problem of fluid flow, and then you should also be able to appreciate any other method if you would like to develop it or use it in future for solving fluid flows, or for that matter any other phenomena in engineering. Okay, so about the logistics of this course, as you must be aware from the schedule, we have been assigned 2 teaching hours. These are on Tuesdays and Thursdays starting from 5:15 p.m. Till about 6:30 p.m. So there are only 2 hours every week, and I would like to pre-record all the lectures and put them online through one of the portals, and you can access them. And then to have more discussion on these material, we can actually use these hours, either one of them or both of them every week, to hold a discussion hour, or for that matter if I would like to have certain evaluations like maybe short quizzes or maybe to discuss the term papers, this is an hour that is available to us and we can use this. If you have any doubt about the material which is going to be available online, you can, of course, you are most welcome to discuss them in the discussion hours, but you can also contact me by the phone number that was in the previous sheet, or you can write an email to me and we can have a discussion on email or in person. Okay, a little bit about the course content. So as I spoke to you just a while ago, the fact that we are interested in a numerical solution already implies that we are okay with incurring some error, but we need to have a bound on the error. So suppose I want to predict on the trajectory of, let us say, an airplane, okay, and it is going to be affected by the airflow, and I want to predict where the airplane is going to land, let us say in a cross flow environment. So there is an error that I have, a tolerance that I have for the error, and I should know that what does my method do or how tight are these bounds. Okay. So, what we are going to look at first is we are going to take a small toy problem. In fact, it will not be a partial differential equation, it will be a very simple ordinary differential equation. And then we are going to talk about the error of the numerical solution versus the exact solution, and then we will try to see how we can control this error, okay, how we can set up a formulation whereby we can talk about where the error is and how to minimize the error and so on. In fact, that is what will set us in a framework where we can distinguish between different kinds of methods. So, you must have heard of these methods like the finite difference method, the finite volume method, the finite element method. So, if we had to argue that how are these various methods connected, this actually would be the framework where we would see how one method differs from the other. Next, what we will do is we will take some very simple finite difference method, very classical methods, and I will try to convey to you what is numerics all about. Okay. So, when you discretize a problem numerically, how does the error change when you increase your resources, okay, and so on and so forth. What happens in one dimension, how do you generalize things to multi dimensions like 2 and 3 dimensions. So, some very simple ideas just to get us started, both in terms of writing simple programs as well as getting familiar with the terminology. Then we move on to the topic number 2, where we will take a simple one dimensional boundary value problem and talk about the solution of this problem, which is the exact solution. And then we will also formulate it in an integral form, which is called as the weak form, and then we will see what happens to the boundary conditions. Okay. So, some of these boundary conditions would be the Dirichlet type conditions, some would be the Neumann conditions. So, what happens to them, that is what we will look at in the first part of this module. We will also show that you can actually take a problem in the strong form, which is essentially the differential form of the problem, and show that it is equivalent to the weak form. We can also show that the weak form is the same as the strong form. So, they are actually synonymous, and depending on what method you want to use, you could either start from the strong form of the problem or the weak form of the problem. And then we will come to the basics of the finite element method, the foundation, which is actually the Galerkin's approximation. So, this is the first time that we will actually talk about the finite element approximation of a simple one dimensional problem. Okay. And we will see that, as in other numerical methods, most of the time is actually consumed by the solution of a linear equation system. So, the beauty is we start with a simple ordinary differential equation, and by using the Galerkin's approximation, we will reduce the problem to something like Ax equal to b, okay, just a simple system of algebraic linear equations. Then we will study a little bit about the kind of approximation it is. So, we are going to use linear finite element space. We will talk about this in more detail as we move along, and then we will talk about some ideas of how to put it in a framework where things are more efficient. So, it is one aspect of a numerical method to design an algorithm, and it is yet another aspect how to do it efficiently. Okay. So, in this course we are going to look at not just the algorithms, but also the framework in which these can be implemented in an efficient way. So, I will show you some ideas about what is meant by an element point of view. So, the name finite element roughly implies that you are going to take a domain. Let us say your domain is a 3-dimensional domain, maybe it could be the room in which you are sitting, and you are interested in looking at the analysis of the flow of air in this room. So, you would discretize this room into elements, okay, many elements. So, that is the element we are talking about. So, we look at the element point of view, and how do you assemble information from all the elements to get various equations, which in fact you are going to eventually solve to get your final answer. Okay. So, there is an element point of view and there is an equation point of view, and we learn how to move back and forth between them. So, this would be done in one dimension, okay, just with a toy problem to give you a flavor of the most basic finite element approach, and as I said, the foundation is the Galerkin's approximation. Next, we are going to worry about, can we generalize this in 2 and 3 dimensions. So, that is the module number 3. So, we will complicate the problem a little bit more, in the sense that now we will go to first 2 dimensions. So, now we are necessarily going to deal with a partial differential equation. So, suppose you look at the heat conduction equation. In 1 dimension it would be just heat conduction in a bar, whereas in 2 dimensions it would be heat conduction on a plate, and maybe in 3 dimensions it would be heat conduction inside a solid object, and so on. So, we will take an example from the heat conduction problem. We will also generalize it to essentially linear elasticity and also some aspects of fluid dynamics. Okay. So, we will look at compared to 1 dimension, what are the complications in terms of the equations themselves as well as the boundary conditions. In fact, what we will see is that even approximating the boundary is going to be a challenge in multi dimensions. So, just to make you appreciate, if you think of a problem in 1 dimension, then the boundaries are actually 2 points on either end of that domain. But when you go to 2 dimensions, for example a plate, then your boundary is a closed curve. It could be a circle, it could be a rectangle, so it may have corners. Okay. And then when you go to 3 dimensions, then your boundary is actually a surface. Okay. So, there are problems even in approximating a boundary. Just to give you an idea, if I had to model, let us say, flow around an airplane, then even to model the surface of an airplane is a big challenge, okay, because a surface of an airplane could be extremely complex, and to be able to put grid points on the surface and then join them via some elements is not so trivial. In fact, the modeled surface that you may get could be a little bit different than the actual surface of an airplane. In fact, even a sphere. So, if I had to model a sphere using finite elements, and let us say I want to use some kind of linear elements, I would realize that I have approximated the surface of a sphere with a multifaceted polyhedra. So, it is not a smooth surface anymore, it consists of some panels. Okay. And so, there are issues in applying boundary conditions and so on. So, we will refer to those issues in module number 3. Next, we go to the module number 4, where actually we are going to talk about the generalization of what we learn up to module number 3. So, we are going to talk about a family of elements called the isoparametric elements, which essentially means that the way you approximate the geometry and the way you approximate the solution itself is of the same order. Okay. So, you use very similar ways to not just approximate the geometry, but also your solution. Think of the following. Suppose I am interested in looking at flow past a sphere, and to represent the sphere I could say, well, the surface will be represented by higher dimensional panels, not just linear panels, not just straight panels. Okay. But the flow I would like to represent with linear elements. So, I could have higher order elements for the surface and a little bit lower order for representing my solution. So, that is not isoparametric. Isoparametric would be if I use linear for the geometry, then I use linear for my solution space. If I use quadratic for the geometry, I use quadratic for my solution space. So, isoparametric obviously is a little bit simpler than either subparametric or superparametric, and then we are going to look at some programming concepts, okay, how to implement them in an efficient manner. This will bring us to the idea of, in 2 and 3 dimensions, generalization of linear elements. So, linear in 1 dimension would become bilinear in 2 dimensions, and it would become trilinear in 3 dimensions. And suppose I want to go to even higher order approximations, we will look at that aspect also. Having done that, because we are in the framework of a weak form, which is, as I said, an integral form of the differential equation, we will soon realize that exact integration is not possible. So, we will have to go to numerical integration. So, there are some rules that you are familiar with, like the trapezoidal rule, the Simpson's rule, and so on. And we will realize that maybe they are not the best. Okay? So, the optimal rules are actually a little bit different. So, we will introduce the concept of numerical integration. Gauss quadrature is one method, which is, I will show you, it is very efficient. And then we will move on to the concept of what is called a shape function, the finite element functions, and how to compute their derivatives. So far, if you go up to module 4, you should be able to look at a linear partial differential equation, but steady. Okay. For example, steady heat conduction in 2 and 3 dimensions, you should be able to solve that problem by the end of module 4. Next comes the idea of what happens if you have unsteadiness. Okay. So, you have time dependence. So, it turns out time is a little bit different than space, and you can guess why. In space, I can move in either directions. So, if I have a positive x axis, I can go in positive x, I can go in negative x, there is no problem. But time does not allow me to do that. I cannot go back in time, I have to respect causality. Okay. I cannot go back and fix things, time always moves forward. So, the numerical treatment also is a little bit different. You cannot do the same treatment for space and time. So, in module number 5, we are going to learn about how to handle time discretization. Okay. So, we will take the same problem as we had taken earlier, the toy problem, let us say in 1 dimension, but now we will add an unsteady term to it, the time evolution term. And we will see if we now apply the Galerkin's method, including that to the time dependent term, then how can we approximate it. Okay. So, we will look at one method. There are of course many methods to look at the time dependence, but I will show you one, which is the generalized trapezoidal method. It is a family of methods, and it has some free parameters like a quantity called alpha, and we will see that for different values of alpha, the method, the trapezoidal method, could give you different levels of accuracy, but it also has implications on the stability of the method, okay, stability of the error. So, we will use that module also to understand what is meant by the stability of an algorithm, what is meant by the accuracy of an algorithm, and in fact what is meant by the convergence of an algorithm. So, as you will appreciate, what I really want is from my numerical method, that if I solve a problem using, let us say, some resources, computational resources, and I now double the number of resources. So, suppose I was using 100 hours of a computer time to solve a massive problem, and now I say I would like to use 200 hours of computer time. Earlier I was using some approximation which used, let us say, 10 GB of RAM, and now I am allowed to use, let us say, 32 GB of RAM. Then obviously as I use more resources, I must get a better solution. If I come up with a numerical method where my error seems to blow, it seems to increase as I use more computer resources, obviously that is a bad method. Okay? So we will look at issues like convergence, accuracy and so on, both in space and in time. And I will show you that not all algorithms have desirable properties. So we must use only those algorithms which have these at least basic desirable properties of convergence, consistency, accuracy and so on. So we would have then done a linear problem, both steady and unsteady, and before we go to incompressible flows, the fluid flow equations, there is one topic that we would like to introduce, and that is how to deal with non-linearities. So I will give you a few lectures on how to deal with non-linear problems. So you are already familiar with a method like Newton-Raphson, okay, maybe the secants method. So we will briefly go through those and look at what are the limitations of those methods, when do they work, when do they not work, and then we will be ready to go to incompressible flows. Now these are extremely complex problems. So if I compare a flow problem, let us say with incompressible equations, to a heat conduction problem, then the challenges are quite complex. So as you are aware, the continuity equation makes a big challenge. Okay? As you are aware that in the incompressible flows, the pressure term is one order lower than the viscous term, which actually is driven by the velocity. So these kind of incompatibility between the order of the various transport terms in the equations, they also have implications in what is the order of representation that I can use numerically. Okay, in the sense that if I am using, let us say, second order terms for velocity, and I try to use a second order term for pressure or a second order approximation for pressure, you can see there could be in principle some problems because the order of derivative is different for the two. So then how do we deal with that? Okay. Also what happens that when you have a convection term, it kind of changes the nature of the transport. So the diffusion term, which is actually the second order term, is more like an elliptic operator, whereas when you include the convection term, then you would not remain elliptic anymore. And how to deal with those, we will actually look at these items in this module.